All right, everyone, thanks for coming. Welcome to the first session. So first up, we're going to hear from Bryan Gaensler. And just for everyone who's speaking in this session, I am sitting here. It's not directly in your line of sight, but I'll give you like a 2-minute warning. And then if you really run over your time, I will stand up and walk next to you dramatically. In 5 minutes for discussion. Great. Okay.
All right. Hello, everybody. Welcome to the Galaxy Workshop for another year. Many of you have come to this workshop many times, and for some of you, this is your first time. And I know from others that I've spoken to that it's a bit like a family reunion, and a lot of you have spent a big part of your careers and got many of your scientific ideas from these workshops. So my name is Bryan Gaensler, and I am the Dean of Science here at Santa Cruz, and it's my pleasure to welcome you to the campus and welcome you to this workshop. So just a little bit about our division. We have 9 departments broadly grouped into 3 categories. One of the jewels in the crown is our astronomy and astrophysics department. We also have math, physics, planetary sciences, a bunch of biology departments, ocean, chemistry, and so on. As well as our 9 departments, we have a bunch of programs and institutes and other things. I just wanted to highlight 3 special units that we have here in our division. One of them is our Science Communications program. This is a unique, world-renowned program. It's a master's program for science journalists. And so a lot of very prominent science journalists, many of whose work you probably read regularly in Nature and Science and Scientific American and so on, they came through this program to hone their craft. We are the headquarters for the University of California Observatories. This is across the UC system, runs the UC component of Keck. Lick Observatory represents UC on the TNT and so on. And a lot of the work and the instrumentation development and workshops are all right here on campus. And finally, the University of California has a large network of natural reserves. These are essentially national parks, but owned and run by the university. 6 of those natural reserves are run by UCSC. These are extraordinary places with unique fauna and flora, and our students get to do incredible fieldwork at these reserves. I went to one of the classes run on the natural reserves at the start of the fall semester this past year. There were freshman undergrads, and I was pretty sure from their reactions that they had never been outside before. And it's just an extraordinary chance both to discover just everything going on and to do research for the first time in a very controlled environment. So here we are by the numbers. Our division has about 200 professors, 52 different degrees, about 4,000 undergraduates, and about 570 graduate students. And I think what makes us unique is that we are both a Hispanic-serving institution and an Asian American and Native American Pacific Islander institution. And so we're one of only, I think, 3 major universities to have both those distinctions. We have a very diverse undergraduate body with a very large number of Pell Grant students, first-generation students, and Hispanic Latinx students. And we do fantastic in terms of our grants, bring in more than $100 million a year in research grants and philanthropy. And those of you that are from Santa Cruz, you're already sick of hearing about this, but I'm going to keep talking about it. I've been in the job for a year, and I'm pushing sort of 3 pillars to sort of take the science division to the next level. We are focusing on research impact. That is research not just where you write a paper and 6 other people read it and say that was all right, but actually research that makes a difference for our community in the world. And here is work that we're doing on actually rebuilding coral reefs that have been destroyed after storms. Given the unique things that we have here in terms of our reserves and Lick Observatory, I'm also pushing degree-defining experiences. Most of you can recall a moment as an undergrad where one professor or a class, there was something where you went, oh my gosh, and that moment changed your life and you suddenly got it and you got that fire in your belly. We want that to be a contractual guarantee, that every student who comes here, we guarantee you that you will have that moment during your degree. And here are some of our students, a week after starting here, actually using Lick Observatory and discovering things. And like every university, we think that diversity, equity, and inclusion are important, but we don't just want to advance them through effort, which is a lot of work and a lot of tiring, hard work to push that boulder up the hill, but to make it part of our DNA, to embed practices so that a lot of the DEI work just gets done because it's part of the way that we do business. So that's a very brief overview of the science division. And I'm now going to change hats because I'm also an astronomer. And Joel invited me to, I haven't hijacked my introduction talk, I promise I was asked to do this, just to tell you a little about the work that I'm doing. So I'm a radio astronomer, and at the moment I'm working on fast radio bursts, which in my 30-year career is the most exciting thing that I've ever worked on. And I just want to give you a very brief sense of just a tiny fraction of the things that are happening on fast radio bursts. So it's very easy to explain what a fast radio burst is, because pretty much everything we know about them is that they're fast, they're in the radio, and they burst. We do not know what they are. They were discovered in 2007, and so over 17 years we have been putting a lot of time into them, and they're still essentially a mystery. There aren't that many topics in astronomy where we really are completely confused 20 years after they were first discovered. So they're bright, more than a Jansky, which is a lot. They're very frequent. There's about one happening randomly in the sky every 2 minutes. They're quite brief, typically a millisecond or so. And we now know that with one exception, we have seen one in our own Milky Way, but all the others are extragalactic at redshifts of sort of local volume out to sort of a redshift of 1. So here's a typical fast radio burst. It goes up and it goes down again in just a few milliseconds. So 10 years after they were discovered, we had, after a lot of hard work, even though there's been one every 2 minutes, presumably for the whole of human history, we'd only found 15. 14 of them had only ever been seen once, and there was this sort of view that that's some sort of explosion that destroys whatever the object is. But then in 2016, one fast radio burst was shown to repeat randomly. And that suddenly produced a big swing in our understanding. We only had one that repeated out of 15. But then people said, well, okay, maybe they're not cataclysmic. It's some sort of flaring event and an object that can recharge and do it again. Because that object was able to repeat, people were able to wait for it to repeat and then hit it with very high resolution radio interferometry and localize it very precisely. And it was found to sit in a low metallicity dwarf galaxy with very high star formation rates. These are the same hosts that people see for long gamma ray bursts and superluminous supernovae. So there was an immediate sort of bandwagon effect where everyone said, oh, well, this is what all fast radio bursts must be. They are something, perhaps the gamma ray burst event itself or something before or after that produces a fast radio burst. So that's where we were in 2017. We just had 15 of these objects. Like we knew each of them individually, like it was a big deal. You would publish a paper reporting one fast radio burst. But the game has completely been changed by a telescope that I've been very fortunate enough to be a part of, the Canadian Hydrogen Intensity Mapping Experiment, which is a software radio telescope. It has no moving parts. It's in Penticton in British Columbia, and it looks like 4 big skateboard ramps. It's quite large. It's, I think it's 80 meters long, and each one of these is 20 meters across, or as they say in Canadian units, it's the size of 5 ice hockey rinks. And its field of view is very large. It doesn't move. It just stares straight up. And this red strip here is the field of view on transit, and you just point straight up and let the sky rotate overhead. So the instantaneous field of view is quite large. It's 240 square degrees instantaneously, and since you observe 24 hours a day, you just let the sky rotate overhead, and you cover the entire, a bit more than the entire northern hemisphere, 24,000 square degrees every 24 hours, which is much bigger than these other exciting survey instruments in the optical and in the radio. So each point on the sky passes through the field of view for about 10 minutes a day, and so during those 10 minutes you might catch a fast radio burst. And so this has been extraordinarily successful. We've been finding about 3 fast radio bursts every day since 2018, which means that we've found about 5,000 fast radio bursts altogether. About 95% of every known fast radio burst has been discovered by chime. We get full polarization. We get an octave of bandwidth, 400 to 800 megahertz, and we get nanosecond time resolution. In fact, the only thing you might think this just completely tells you everything you need to know, the one catch is that the spatial localization is relatively poor. We only know where a fast radio burst is to within a few arc minutes, which is not good enough to localize it and tell its host galaxy. But here are an example of 8 of the thousands of fast radio bursts. So from left to right on this plot is time, and from top to bottom, or from bottom to top is frequency. We call these waterfall plots. And here are 8 different fast radio bursts. You can see they're all slightly different. both in their profiles and also in their time frequency structure. So again, just to put things in perspective, here's a graph of number of fast radio bursts versus time. Orange is everybody else, and blue is chime. And you can see that unless you're talking about localizations, which other telescopes are good at, chime is essentially almost the only game in town. It's just been spectacularly successful. So what can you do with a fast radio burst? Well, that could be an entire conference, and indeed we have entire 5-day conferences just on fast radio bursts. But I'm just going to give you like the snapshot version. So in order to discover a fast radio burst, you have to correct for the dispersion of the intergalactic medium. So radio waves don't quite travel at the speed of light because of free electrons in the interstellar and intergalactic medium, and the amount by which they're delayed is frequency dependent. The high frequencies travel faster than the low frequencies, which means that if you just observe over a range of frequencies, the burst arrives at different times at different frequencies, and the signal gets smeared out. So the way we search for fast radio bursts is you take some chunk of data, 10 seconds, and you correct for that dispersion at every possible delay. So it's quite a computationally intensive process. We have to have a supercomputer on site. You search for all possible dispersions and find the one at which the signal to noise suddenly jumps out at you. So here's what the actual signal looks like, the raw signal arriving into a telescope, and you can see it's smeared out. If you sum this vertically, you wouldn't really see anything, but if you correct at the right dispersion, you get a nice signal. So the dispersion is simply the slope of the t to lambda squared, and it turns out that if you work through Maxwell's equations, it's exactly equal to the integral of the number of free electrons along the line of sight with a redshift correction. So simply to even discover a fast radio burst, you have to know exactly how many electrons there are along the line of sight. So that's annoying in terms of the computational work that you have to do to find them, but it's fantastic because it means just the mere fact of being able to say, I found a fast radio burst, you've made a very interesting statement about its foreground. So this number, the number of electrons along the inner sight in units of parsecs per cubic centimeter, is called the dispersion measure, the DM. And so every fast radio burst has a DM normally calculated to better than 1% precision. So before you do anything else, before you start looking at subtle statistical properties or host galaxies or anything, chime has 5,000 fast radio bursts, each with a dispersion measure. And you can do all sorts of things with that. I'm just going to focus on something relatively simple, which is if you can localize the fast radio burst and therefore find its host galaxy, then you also have a redshift to the galaxy. And you know that Hubble, of course, had two pieces of information. He had redshift and velocity, and he was able to do rather interesting things with that. We can do our own version of the Hubble diagram, which we call the McCart relationship, where instead of plotting redshift versus recession velocity, we can plot redshift versus dispersion measure. And so since the dispersion measure measures how many electrons you've passed through, you'd expect that as you go to higher redshifts, the dispersion measure should go up. And in the relatively local universe, where you don't have to worry too much about complicated cosmological effects, it should just be a linear relationship. You double the distance to a fast radio burst, it goes through twice as much stuff, and the dispersion measure should be twice as high. And therefore, the dispersion measure should be a very useful distance and redshift indicator. So it's really hard work to localize a fast radio burst. Most telescopes don't instantly give you that localization. You have to do all sorts of follow-up. But eventually you get something like this. So here is that little green circle is a fast radio burst that was discovered by Chime with a huge error circle and then eventually localized. And you can see it's sitting in the arm of a nice spiral galaxy. So we've done that for the thousands and thousands of fast radio bursts discovered. We've done this about 30 times. And you can take those 30 host galaxies and you can plot the dispersion measure versus redshift. You do have to make a correction in that some of the dispersion measure is from the Milky Way, so you have to subtract that off, and you're left with an extragalactic contribution to dispersion measure, and you plot versus redshift. And so you get this relationship that you call the McCart relationship. And of course, every one of you, you're an astronomer, there's this overwhelming, unquenchable need to fit a line to these data. So you do that, and you get this. So you might think, that's not a very good fit. You need to draw a better line, but that's actually not a fit to the data. That's what prediction you would get if you take concordance cosmology. If you take the best estimates we have of omega baryon and the Hubble constant, then you get that blue line. So your first reaction is, well, that's not too bad. It looks like cosmology's okay. And so the exciting thing you can conclude is that you are directly in, I don't think most people think the baryons are missing anymore, but the missing baryons you can clearly see are there. Just the right number of baryons to add up to what you expect is all there in the dispersion measure. The intergalactic medium is indeed containing all of the electrons and atoms you need to make up the missing baryons. But what's more, you might say, well, this isn't a great fit. Surely you can do something a bit better. And why it's not a great fit is you can see that there are many more red points above the line than below the line. And that's not a crummy fit. It's not telling you anything profound about cosmology. It's actually telling something very exciting about galaxies, which is what we're here for this week. You can see that most of the red points lie above the line, and that's because you are measuring the dispersion measure of the host galaxy. The fast radio burst is sitting in a spiral arm. There are clouds of gas and other things, and it's traversing through those as well as through the intergalactic medium. So statistically, this excess is telling you something about the electron content of the host galaxies of fast radio bursts. So here's the McCart relation. We've established pretty clearly that it's sort of roughly a linear relation out to sort of lowish redshifts. But what's exciting is that you can take this a bit further. You can actually model the scatter, not due to the host, but there's also an extra scatter due to the intergalactic medium, which isn't uniform and has a different amount of electrons along different sight lines. And so you can do quite a complex analysis where firstly you can pull out Hubble's constant just directly from these data. And from the sample we have so far, it's about 85. But there's some systematics in that we're still understanding, plus the error bar is going to come right down as we get more fast radio bursts. And you can also quantify the actual variance of the clumpiness of the intergalactic medium along different lines of sight. So this is really just, I think, a proof of concept at the moment. It's very early days, but this is going to get much more exciting as we get larger numbers of fast radio bursts. And then the last thing I wanted to point out is just looking to the future, we can actually study the epoch of reionization with fast radio bursts. Not the epoch of reionization that most people like to talk about, which is this one down here, but we can actually study the epoch of helium reionization when quasars completely ionize helium at a redshift of roughly 3. And that is because we believe that there are fast radio bursts at redshifts much larger than 3, and we have their dispersion measures, and we can look at the way in which dispersion measure evolves with redshift. So here are some theoretical calculations of what you would get from dispersion measures of fast radio bursts. If reionization happens exactly at redshift of 3, then you get this black line, and you can see that if it happens later, then you get a little bit excess dispersion measure because you get more free electrons from helium later and later in the earlier and earlier in the universe's history. And this is just plotting it in a different way. This is plotting the number of fast radio bursts dm, and the red is the percent difference between an early and a late reionization models. And you can see that at a dispersion measure of about 4,000, there's about a 15% difference in dms between a universe where helium reionization happened at a redshift of 3 and helium reionization happened at a redshift of 5. So that's at a dispersion measure of about 3,000 or 4,000. You can see on this plot that these are only about 1,300. So you've got to go way, way off the top of this plot in order to start probing helium reionization. But the exciting thing is that we do actually have fast radio bursts that have these very high dispersion measures. These particular fast radio bursts don't have accurate localizations, and therefore we don't know their host galaxies or their redshifts. But there are 2 published faint fast radio bursts that have dispersion measures of more than 3,000 parsecs per cubic centimeter. So here's one of them. You can see it's faint. Here's the fast radio burst. And if you interpret this dispersion measure as being purely due to the intergalactic medium, then this is a fast radio burst at a redshift of about 3. What's more, we have thousands and thousands of unpublished chime fast radio bursts. There's a lot of work to get it into the data quality needed to publish it. And of those, we have dozens of fast radio bursts with dispersion measures of much more than 3,000. So there is clearly a modest but growing population of fast radio bursts with very large dispersion measures that potentially put them at redshifts where their dispersion measures could probe the epoch of reionization. There's a catch, but because as I said before, the signal that you measure is just the sum dispersion of every electron along the line of sight. And so not only are you getting the Milky Way in the intergalactic medium, but you're also getting dispersion measure from the host. And so essentially the vertical difference between these red points and the blue line is some combination of variance in the intergalactic medium, but also the host galaxy. And so you can see for a couple of these, there's a significant dispersion measure contribution from the host. And there is a couple of other fast radio bursts where we think there could be dispersion measure contribution of the host of more than 1,000 parsec per cubic centimeter. So when we see a fast radio burst with a very high dispersion measure of 3,000, either it's at a very high redshift or it's at an uninteresting redshift, but it's embedded in some very complicated, dense environment. And at the moment, we don't know which one. So what I'm doing with a postdoc, Mike Walmsley, is trying to distinguish between those two. The ultimate step would be to have an enormous conga line of fast radio bursts, all with known redshifts, all at higher and higher dispersion measures, all lined up. But in order to probe reionization, you would need something like 5,000 fast radio bursts at high redshift, all with redshifts and hosts. And we're probably 10 years away from being able to do that. So in the meantime, we're trying to do this statistically and just asking a simpler question: what produces high dispersion measure fast radio bursts? Are they high dispersion measures because they're at high redshift beyond the epoch of helium reionization, or are they at high dispersion measure because of their complex hosts? And so just simply, if they're at high redshift, then from a statistical sample, you'd expect to see the manifestation of high redshift in their fluence and in their burst widths. Just cosmological effects would make these bursts systematically longer than ones at low redshift. And if it's all due to their hosts, then you would expect to see excess scattering in these bursts that you might not see for the purely intergalactic medium sample. So the first thing we're doing is we're taking a very large sample of very faint bursts, too faint to be classified by our team, and farming them out to the internet. And so through a Zooniverse interface like this, a user gets to look at this and decide whether it's real or it's radio interference and classify events. Every event is being classified by at least 10 citizens, which means that we can basically assign a probability to each event as to whether it's real or spurious. And so far we have hundreds of events from this effort, all at high dispersion measures and with a probability of being real of more than a half. So we're now doing a detailed analysis. Here are some of the events that our citizens have found. They are faint, but we're pretty sure that they're real. We have sneaked them into the main professional pipeline and seeing if the astronomers also think they're real. And here's one, here's another, and you can see the dispersion measures are very high. So watch this space. We're hoping to at least establish whether high dispersion measure fast radio bursts are probing the epoch of helium reionization, and therefore whether we can actually use them to study that epoch. So to wrap up, there's really a revolution in radio astronomy happening around software telescopes. They let us look at the whole sky all the time with everything, with full polarization and broad bandwidths and high time resolution. We've built such a telescope, finding thousands of fast radio bursts. We're probing the intervening gas. I haven't talked about magnetic fields, but we learn about intervening magnetic fields too. We're hoping to use them to trace helium reionization. And then I haven't talked about this at all, but we're hoping to, of course, figure out what fast radio bursts are. There's still a feeling that it's some sort of flare from a magnetar, but I think there's a lot of evidence that there might be multiple types of different objects that are producing fast radio bursts. And finally, this is just the beginning. CHIME is about to turn on its outriggers. These are little baby chimes that are thousands of kilometers away, so we'll get a milliarc-second localization to every one of those fast radio bursts, 3 a day. There's other telescopes being built like CHORD and the DSA 2000, and into the next decade, we're going to sort of leap a whole magnitude up with the Square Comet Array. So I hope I've captured to you this is a really exciting field. We still don't know what fast radio bursts are, but nevertheless, they're telling us a lot. Thank you.
Great. All right, thank you so much. That was really, really interesting. We have time for probably one question, and oh man, you guys. No, I saw your hand first. Please don't ask a question until you have a mic in front of you.
Could you say a bit about how you're planning to disentangle systematic galaxy evolution trends from helium reionization when you're looking at sort of these trends over time at high redshifts?
So I missed the last part of that. You said how are we going to disentangle it at what?
A galaxy evolution trend, so systematic redshift trends to galaxy properties from helium reionization.
I don't think I can say that yet. We're still at a very early stage in this process. We recognize that other researchers like those in this field have been thinking about subtle effects like this for a long time. The first step is just to establish whether we're even at those redshifts yet. If these are all just local galaxies with complex hosts, then going to be a long time. We'll have to have telescopes that are much more sensitive to get to these redshifts.
All right, I'm going to let Mark ask his question while...
That's actually okay. I got the exact same.
Oh, the exact same question. Okay, great. All right. Well, let's thank Bryan again, and let's have our next speaker come sit up.
Thanks very much, and have a great